Optimizing Query Performance, Eager Aggregation. In Arcadia Enterprise Release 4.2, we introduced eager aggregation, which accelerates queries that operate on datasets with star schema architecture. Eager aggregation relies on analytical views and referential constraints. The star schema is used widely in business intelligence. It gets its name because its physical model resembles a star shape. At its center, it has a very large fact table, and the dimension tables around it represent the star's points. The star schema separates business process data into facts that log the measurable quantitative data about a business and dimensions that further describe attributes related to fact data. Here we have a store sales fact table and 9 dimension tables: date, time, item, customer demographics, household demographics, customer address, store, and promotion. The store table describes the store, where it is located, number of employees, floor space, opening and closing hours, and so on. The item dimension table provides the information about the product sold at the store: product description, category, sales price, wholesale price, supplier, and so on. Star schemas are generally a tricky problem to solve in business intelligence because star queries, or queries against the star schema, do not reduce the number of records. Typical aggregation joins are reducing. The join result is much smaller than either of the tables. Contrast this with star joins. The star join result has as many records as what you selected from the fact table, because every transaction that appears in the fact table has multiple keys that join it with dimension tables and add more information. Every row in the store sales table necessarily has a match in the date table, in the time table, and so on. For example, the item table has unique IDs for each item as a primary key. However, that same ID repeats in the store sales table many times as part of many purchases. Therefore, star joins are not reducing joins. In fact, they produce the equivalent of a wider table with the same number of records. The eager aggregation feature enables us to accelerate star queries by using referential integrity constraints and analytical views. Here, we exploit the relationship between the keys of the fact table and the dimension table. These keys are also known as foreign key and primary key pairs. Let us demonstrate how to construct a dataset. We are working with the TPC-DS benchmark data. The fact table is store sales, and we're making a sample join between the store sales and item tables on the item ID. Next, we show sample data from the join. Next, let's build some reports on this dataset, where visuals use the star schema query. The clock shows that it takes a long time to view this report, nearly 5 minutes, which is a very long execution time. The administrative interface shows you the duration of the build. You can also note that we are not using analytical views. Remember that when a dataset has a join, it can use existing analytical views by associating a logical view with this dataset, and then creating an analytical view on top of that logical view. Note that such analytical views are not incrementally refreshable. In typical BI environments, the fact table continues to grow, adding records with each new transaction. Dimensions also continue to change as we add more inventory and as new customers start shopping at the store. From that point of view, computing this join and keeping the analytical view fresh is a resource-consuming process, and it is a slow process because it is not incrementally refreshable. Let us examine the graphical plan from the bottom up. We can see that the join used the hashing mechanism. The inner side of the join is the build side. We want to hold it in memory, so the smaller table is typically on the inner side of the join. In this case, it's the item table, and we can see that we're reading 48,000 rows to build the hash table. The outer side is the probe side. In this case, it's the fact table, store sales. We are reading some 8 billion rows. For each of these rows, we're probing the hash table for matches in the item table. This data is then aggregated, and as the colors indicate, this is one of the slowest operations in the plan, taking 3 minutes and 41 seconds. In query details, you can see the original query. In order to exploit eager aggregation, we have to define referential integrity constraints, or declare the foreign key primary key pair. Let's go back to the dataset join modeling screen, where you will see foreign key boxes on each side of the join. When you pick foreign key on one side, it automatically sets the other side to primary key. Keep in mind that when you define this relationship in the dataset modeling interface, this relationship is between the tables. Therefore, any other dataset that uses the same table with a join on the same columns also benefits from the referential integrity constraint declaration, and therefore from eager aggregation. Conversely, if you drop the referential integrity constraints from one dataset, other similar datasets lose the benefits of eager aggregation. Now, after we define the foreign key and primary key constraints, we're ready to accelerate our reports. Let us pick the dashboard to accelerate. In order to see actual recommendations, click the Get Analytical View Recommendations button. We have 3 visuals, and it is evident from the naming that all of them can benefit from the same analytical view. When you click to see details, the recommendation shows the rating of the proposed analytical view or how much benefit this analytical view provides in improving the performance of a query. Several factors go into deciding the star rating. The first item is whether the base table is in a format other than Parquet. If an analytical view is Parquet, then there's a clear benefit in reading the data from a Parquet file. Secondly, does the analytical view materialize joins? Then your query is going to run faster because you have avoided competition at query time. If the analytical view reduces cardinality, then you're getting the benefit of data reduction, which is a good thing. If the analytical view is incrementally refreshable, it's going to be faster, which is highly desirable. All these factors play a role in deciding the star rating. Next, let us look at the base table information tab, which shows the file format of the base table, how many rows it has, row size, in-memory size, on-disk size. You can see that there is a difference between in-memory and on-disk size. On disk, the table may be stored in a compressed format, so it takes less space. When it is read into memory, it is uncompressed and it takes more space. We can also see the partitioning columns of the base table. The next tab shows analytical view information. Most of the information here is similar in what we saw in the previous tab. However, the size of the analytical view is an estimate, the row count is an estimate, and we evaluate the in-memory size as an estimate. We do not display the on-disk size because we cannot estimate the compression rate of the data. The last tab shows the visual sequel. Which visuals benefit from the analytical view that we're examining? At the top, you can see the ID number of the visual. So IDs 95, 97, and 98 will all benefit from this particular analytical view. The SQL query that corresponds to those visuals is also here. Now, let us refresh the analytical view. As you can see, the refresh takes some time, 2 minutes and 34 seconds. Initially, when we did not use analytical views or eager aggregation, we were paying the penalty of evaluating the join and expensive aggregation every time we loaded a report and every time we ran the query. Now, with analytical views and eager aggregation, we're performing this task only one time. In the analytical view refresh, we're not computing the join every time. Instead, we calculate the expensive aggregation up front as part of analytical view refresh. Later, as you load the reports or run the queries, you can use this free cache data again and again, and that is where we reap the benefits of this optimization. We recommend that you schedule a regular refresh for your analytical views. Let us load the reports again. Notice how fast they are with analytical views and eager aggregation, just 5 seconds. Let's check the admin port again. You can see the query, and it shows that we used an analytical view. When we examine query details, we see the graphical plan. Now the thing to note here, that again, we have a hash join with the item table on the inner side of the join. It has the same 48,000 rows. However, on the probe side, we are now probing with only 17 million rows instead of the 8 billion we had originally, which is nearly 500 times smaller. It is still an aggregate, the most expensive part of the execution plan, but it has reduced from 4 minutes to 485 milliseconds, just under half a second. This is the real benefit of eager aggregation on analytical views. Let us examine the original query, and then switch to the Rewritten Query tab. It shows the optimized query. Instead of the store sales back table, the query uses the newly recommended and created analytical view. This completes our presentation. Thank you very much.